Hello, everything should be okay now. At the last minute, I realized I copied the wrong file to the web server, so I had to go fix that. You probably noticed. Okay. Okay. I had the wrong file here for the operating systems class up on the web server. Okay. So can you hear me? Everything seem okay?
Yes.
Yes.
Great. Thanks. All right. So today we're going to look at this code for system calls. Okay. So I'll download this one also, just for the heck of it. Okay. Okay, we want to look at how system calls. Let's see, I want to open up the picture. We want to kind of think about this picture here. How does the fact that, oh, not that one actually. We had a more recent. The fact that I/O operations are system calls. So if you want to talk to the hard drive, your program, it calls open file, read file, but open file and read file actually call system calls, call NT open file and NT read file. So these are just calls into the operating system. Remember, that means that they switch from user mode to kernel mode. You're jumping from user mode to kernel mode. This guy actually does the real I/O operation, not your function calls here. Now, it's not these functions that do the I/O. The I/O is not done in user space. Okay. Now, two things are going on here. One is that the I/O operations are slow. So once you ask for read file, the operating system is going to put you in the block state because it takes so long for the hard drive to do its work that the CPU is not going to wait for the I/O operation. The CPU will put you in a block state, start up the hard drive, and then the operating system will tell the CPU, go run some other process. Okay, so the CPU will be running some other process in the run state while the hard drive is spinning and doing your work. Okay, at some point, your work is done. The hard drive lets the CPU know. The CPU traps into the operating system. The operating system updates its data structures, realizes that your process is ready, and moves your process from the block queue to the ready queue, then goes back to working on the process that was scheduled. Okay, so that's one issue here. The other issue here is this jump from user space to kernel space. Okay, turns out that jump is very time consuming and something that needs to be worried about. So we're going to look at code that shows us that this jump from user space to kernel space is a problem. It's something that programmers ought to be aware of. Okay, so here's how we're going to do it. Okay, there's this folder on Windows system calls. And we're going to just write some code that does I/O operations. Okay, let me just extract both of these. I don't know if we'll want to look at the last folder or not. Okay, so look at it. Now we're in this folder here, buffering and system calls. These other two folders are mostly information. This is the one that has the code examples in it. Okay. Okay. So I'm going to download that large text file that we used the other day. So double click this one. It just gives us a text file to use it to do I/O with. Okay, so there's a file to do I/O with. So 6 megabytes. Okay, then here's a C program. Okay, real simple program. It wants to count the number of bytes in standard input. Okay, so what does it do? It's going to use there's 1, 2, 3 versions of this program. Okay, count standard in 1, count standard in 2, count standard in 3. Okay, actually, and then a couple more versions of it. Okay. Okay, so there's a bunch of versions of this program. Okay. Okay. Now let's just see what it wants to do is count how many bytes it can read from standard in before it sees end of file. Okay. So, and this is the Java version. I don't want to look at the Java version of it right now. Okay, so that was the Java version of it. There's actually there's three different. I did this in Java to show you that if you have trouble reading C, you can read the Java versions if you want. But we're interested in the C version. Okay, so there's three different Java versions. Okay, there's three C versions. This one uses the C library. This one uses what's called the POSIX libraries. That would be the library that Linux uses. And this one uses Windows libraries. Okay, so let's look at these three. Let's first look at the C one. Okay. Okay. Here's the function we want. There's the function that reads. That's the user space function in the C library that reads from a disk, a file. Okay, so there's the function that reads from a file. It's called file read. The F in front of something like fprintf prints to a file. Fscanf reads from a file. Fread reads from a file. So in C's way of doing things, if you see the letter F in front of a function call, it means it does something to a file. Okay, so read from a file. Okay, what it's going to do is it reads. There's 1, 2, 3, 4 parameters. The last parameter is the file it's reading from. Okay, the first parameter is where it's reading to. So it's reading from here into this array. That should be an array. Okay, so it should read bytes from here into this array. Okay, then there's two numbers here. Okay, there's two numbers. This one is the size of that array, and this is how many bytes you want to read from here. Now, the function, for some reason, treats these as different things. Now, actually, we should look up the documentation on the function. This is probably a function that you probably not used. This is a pretty low-level function, and it's important that we use like have a low-level function. So let's just look real quick at the documentation for it. Okay. Okay, fread takes 1, 2, 3, 4 parameters. 1, 2, 3, 4 parameters. There's our. Yeah, can I get them? Windows is doing funny things. Okay. One, two, three, 4 parameters. The last parameter is a pointer to a file structure. That means you've opened a file. So you've opened some file ahead of time. Now we're reading from standard in, so we don't have to open that. Remember, every program, when it starts, automatically has standard in, standard out, and standard error. Okay, so every program has standard in opened. So I don't have to open this file. The file's open for me already. So there's the file I'm reading from. Okay, then notice that this thing's a pointer to void. It's an array. Okay, so it's an array that the data from here is going to be read to there. Okay, then you have a parameter called a size t. Size t is a size parameter. It's really just an int, but it's an int that measures the size of something. In this case, what we're measuring is how much data we want to read from here. So this is saying 1 byte. Okay, then there's another size t that says now size t is a type in C for the size of something. It's really just an int, but it really means how many bytes are in something. This is how many bytes are in what this guy's pointing at. This guy we think of as an array, and this is the size of the array. Now, usually you'd put the size of the array next to the array, but they didn't. So there's an array. We call it the buffer. This is the size of the buffer. And then this is how many bytes I want to put in it. You would think that they wouldn't need both of these. And I'm not even sure why they do need both of them. Because if this buffer is 100 bytes long, you're not going to put 200 bytes into it. Okay. But the way it's designed, they want to know how big the buffer is and how many bytes they should read into it. Okay. Right. And then they describe oh no, I'm sorry. It's the other way around. Oh, it is the other way around. I misread it. I forgot. This is the size of the array. So you have to read it. Reads that many items of data. So that's the number of items to read, and that is the size of this array. Sorry, I read it backwards. Okay. So this is saying that this is a array of 1 byte. Okay. And then this is the size. Here I'm using buffer size to mean how many bytes I want to read into that array. Okay. And I got buffer size set to 1 too. Okay. Okay. Actually, I probably put these backwards in my program. I probably have these backwards in my program because I have them both set to 1. So I probably didn't pay attention to that. I should have buffer size there, and I'm reading 1 byte. Okay. Yeah, I'm reading number of bytes into here. Okay. So the function reads that many items of data. Oh, I'm sorry. I should have read this ahead of time. This is not the size of this buffer here. Yeah, they don't need the size of this buffer 2 times. Okay. Yeah, I forgot how this is a tricky function. Okay, now I remember. Okay. Here's the buffer. Okay, they don't care how big it is. Okay. This is how many this is the number of items of data. Okay. This is the number of items of data, okay, of this many bytes. This is the size of the data. So here's how I would think about it. Let me just open another file. Okay. Suppose I want to F read into some buffer. Say I want to read 100 doubles. Okay. Suppose I want to read 100 doubles. Well, a double this would be the size of the piece of data I'm reading. So I would say a double is 8 bytes, and I want to read 100 of them from, say, standard in. Okay? Okay. So this is how many items of that size to read from there and put in there. Okay? How many of that size to read from there to put in there. So this would read 800 bytes. It's going to read that times that number of bytes from there into there. Now notice if this was reading 100 doubles, it doesn't know it's reading doubles. You're not telling it, like, that's the difference between this and fscanf. Fscanf, you can say read a double or read an int. Fread's lower level. Fread doesn't even know it's reading ints or doubles or whatever. It just says you're going to read this many things, each of which is this size, from there. Okay. So for example, if I want to read 100 ints, each int is 4 bytes. And I want to read, I want 100 4-byte things from there and put them in there. And it's up to you to make sure there's enough room in here for this much data. So they don't want to know how big this buffer is. Okay, they don't care about how big it is. It's up to you to make sure there's enough room in it for that much data. Okay, so pointer to your buffer, the size of each data item you want to read, how many data items to read from there. Okay, the function ref reads that many items of data, each size bytes long, from the stream, storing them at the location given by this guy. So from here, read this many things of that size and put them in here. Okay. Then what about the return value? See, notice the return value is another size t. So that a size t is an int, but it's supposed to measure the size of something. Okay. Now, on success returns the number of items read. Okay. Now, what that means is, you suppose I told it to read 100 items from standard in, but it hit end of file after 30 of them. Well, it could hit end of file after 30 of them, so it's going to return 30 to tell me that it read 30 of the items I asked for. Okay, so it's going to return the number of items it read, and if the number of items it read is less than this, you've hit end of file. Okay. Well, returns the number of items read or written. Okay, see, this is both the documentation for F read and F write. They kind of doubled up the documentation here because read and write have parallel structures, so they're doubling up the documentation. On success returns the number of items read or written. This number equals the number of bytes transferred only when size is 1. Okay, it's the number of items, not the number of bytes. If an error occurs or the end of file is reached, the return value is a short item count. Okay, they call that a short item count, a short or just short count. They call them short counts. You asked for 50 things and you only got 27. That's a short count. And you could get 0. You know, something could really go wrong and you get 0. They didn't read anything. Okay. All right. So this is a basic IO function. Okay. This is a real low level. It's really just reading bytes. It's really just a way of saying read this times this number of bytes from that file, from there. Okay. So it's real low level. It doesn't know anything about ints, doubles, struts. It just, now the reason they let you do this thing here about the size of the item and, well, the size of the item and the number of items is that this thing can read records from a database, for example. So I might want to read 10 records, and I know that so I might want to read here 10 records, but I know each record is 57 bytes. You know, so I'm instead of me computing how many bytes that is, they let me do it kind of nicely. I can say how many things of that size I want to read. It really just reads that many bytes. It just takes those two numbers and multiplies them together and reads that many bytes. Okay. But it lets you think of it at a higher, it lets you think of it as slightly higher level. You can think of it as that many items, each which of that size in bytes. Okay. But it won't let you say read 10 ints or read 27 doubles. It's lower level than that. This is a lower level file reading function. fscanf would be the higher. Oh, fscanf is written in terms of this function. If you actually looked at how fscanf works, fscanf is a slightly higher level reading data function, and it calls this lower level one. Okay, so so this is the lowest level of their functions for reading data. Okay, and all the other functions that somehow read or write data, for example, printf actually calls this write function. Printf would boil down, if you looked at the source code to printf would boil down to that thing. This is the low level write data. So printf would print where this thing would be to standard out. Printf would boil down to a call to fwrite where this thing is standard out. Okay, so these two functions are the pretty much, I think they're the lowest level. I'm not aware of anything that's at a lower level in the C library. So as far as I know, these two functions are the functions that all other IO functions are written in terms of, fread and fwrite. Okay, notice it's called binary stream input output. You know, it just thinks of it as a stream of bytes. It doesn't, these functions don't think in terms of ints and doubles and struts and anything high level. They just think in terms of stream of bytes. The basic unit is byte. All right. So here in my code, I'm doing this is my buffer. Okay. My buffer is buffer size and it's 1. So it's one byte. So I'm using a 1 byte buffer. I want to transfer one thing of size 1 byte. So I'm reading 1 byte at a time. Okay. So now I want to count bytes. Remember, the function wants to count how many bytes there are in standard in. Okay, so that's what it would do. It would read one byte at a time. It would read a byte, and then it checks. Notice that it checks that the return value is not 0. Okay, so the return value, because if I'm reading 1 byte, the return value is either 0 or 1. Okay, on success it returns 1. On failure it returns 0. So this would be while not end of file. While essentially this is saying not end of file. Notice it doesn't say end of file, but I know that that's what that means. The only way I get 0 bytes is, well, it's really not end of file. The only way I get 0 bytes is if I hit end of file or something went wrong. Okay, so while I successfully read while this would be read as while successfully reading a byte, add, well, in this case, n is always going to be 1, add 1 to my counter. So I'm counting up the number of bytes. If something goes wrong in the read, or if I hit end of file, I'll get back a 0, I'll drop out of the loop, and I'll print out how many bytes were read. Okay? Okay, so this thing reads 1 byte at a time and counts how many bytes it sees. So let's run the program. Okay, so I'll open a command window here, and I'll just compile it at the command line. So my compiler is in the C:/CS302 folder, and it's in min.gw. It's in the bin folder inside there. GCC is the compiler. Oh, I hit the wrong key. /GCC is the compiler. Okay, and I want to, the output file should be, now I'm compiling count standard in, not Java. Oh, let me make the window longer so you can see what's, I'll go past it. Oh, I want the clib, I want the clib, that's when we were reading, the C library function. And I want the output to be EXE. And I want to compile. Notice I'm using the tab key. So I'm hitting tab key either time. Let it do the typing for me. Okay. So, compile, make the output file this EXE, and compile that file. Okay. So now I've got the EXE version of that file. Okay, so now I can run it. Okay. Now if I just run it at the command line, okay, if I run it at the command line, it's reading from standard input. So I can just type some stuff. Okay, and then I tell it that no more stuff by doing Control Z, hit enter. Okay, and I type 32 characters. Okay, if I do it again, if I type 1 character, Control Z. Okay, oh, why did I type, I typed 1 character. It said I typed 2. Okay, try it again. Run the program. Okay, I type 1 character, X. Then I type Control Z. Why did it tell me I typed 2?
Right, Control Z.
No, what was before the Control Z?
Enter.
Enter, yeah. Yeah, the Control Z wasn't counted. The Control Z was treated as the end of file character, but the Enter key was counted. Now, notice that I can't just get a count of 1 in this case. So if I run the program, I type a letter, how can I get the program to see that letter?
Type Control Z now.
Oh, that's a good guess. Didn't work. Control Z has to be the first character on a line in Windows. It would work on some operating systems, but not Windows. It kind of ignored, well, actually it counted back Control Z. So it's still waiting for me on input. So now let me do a Control Z. The Control Z needs to be at the beginning of the line. And 2 characters. So it did ignore the Control Z. It did ignore it. Okay, let's do it again. Okay, X, Control Z. I've typed 2 characters so far. Enter is a 3rd character. Control Z is the 4th character. I know that one's ignored. So it did not count either of the Control Z's, but it didn't treat the Control Z, the first one as end of file. Notice that when you run little baby programs, you can actually learn things about how your operating system's working. The control Z needs to be the first character on a line, but it's not counted. Okay, so it did not get count like, so let me do another. Here's X, control Z, Y, control Z, Z, control Z, 0, control Z, now control Z. 8 characters. That was X, carriage return, Y, carriage return, Z, return, 0, return. There's control Z's, none of them got counted. But they didn't do what they were supposed to. They didn't do what you expected them to do. They didn't act as end of file. Notice that you learn a lot about operating systems by writing dumb little programs. This is actually one of the most important things I think you can learn in this class, is that if you want to know what your computer's doing, write little programs and test them. You learn massive amounts of detailed information, and these details matter. Little details like, what's control Z really do? Well, it means end of file, but only if it's at the beginning of a line. Well, what if it's not at the beginning of a line? And then it's ignored. So now you know a detail that, believe me, that detail comes up. Go Google Stack Exchange about control Z's, and you'll see lots of people asking questions about what in heck does control Z really mean? What does it really do? And because these little details come up in real world programming a lot. Lots of little details are constantly coming up. Now, here's another thing I can do. I can run my program with standard in being one of my files. Okay. There was 567 characters in that file. I counted cstandardin.java. Well, did my program do the right thing? Did it give me the right number? It said there's 567 characters in that file there. And look, my program agrees with Windows. Okay, 567 bytes. I said characters. Actually, I should change that to bytes, because characters and bytes don't mean the same thing anymore. Characters now can mean Unicode characters, and a Unicode character is not 1 byte. In C, old-fashioned characters are 1 byte. But in modern programming, what people now call characters, is another one of those details that you have to be real careful about. Unicode characters can be anywhere from 1 to 8 bytes long. Some Unicode characters are actually 8 bytes long. So the file is 567 bytes. Okay, and then I can. So I'm measuring the size of a file. So what about my file big.txt? Oh, I thought didn't I download it already? Oh, I misspelled it. Okay. Big.txt. Yeah. Okay. Big.txt 6.4. So you can see I got the right numbers. See how they put commas in that number there? I struggled for a couple hours the other day to try to get C to put commas in those numbers. I couldn't get it. Yeah. And I found one of the longest Stack Overflow questions I've ever seen when somebody tried to ask, how can I get a comma in the output from printf? It was like 50 pages long. Okay. Programming is crazy. Now in Java, it's real easy to do this, to get a comma in your output for your numbers. It turns out that in C, they just didn't think of that. It's not part of printf. So you kind of have to do weird things to get commas in your large numbers. Okay, so they're probably using some other library here to get that number printed with commas in it. Java does it real easily. It's real easy to get commas in your large numbers. In Java, turned out I couldn't. I mean, it just turned out to be a real mess to try to get printf to put commas in a large number. I actually spent a couple hours on it and didn't get it to work. Okay, if you find a simple way to do it. I was Googling, and I literally found a Stack Overflow page that was something like almost 50 pages long, of just answers about how to try to get comma in the output of an integer in printf. If somebody finds a simple solution, I'd like to know how to do it, because it would be real nice to get these numbers to print with commas in them. Okay. All right. Now, what's the point of this? Create this large text file. Okay. So remember, I can use this guy to create the 1 gigabyte text file. So this takes a little while. I should have been running this in the background while I was talking. Okay. Whoops. What happened? Did I run out of disk space? No. Let me try it again. I don't know what, it died on me. I wasn't paying attention. I may have accidentally, when I was trying to drag the window, I wonder if I accidentally clicked on here and closed it. I may have like closed the program. Okay, so let me start over again. Yeah, it's already up to 300 meg. So I want to delete that, download it again. So I don't want to create a 100 gigabyte file. So I want to start with 6 gig. Remember, this program doubles it a bunch of times. So it goes 6, 12, 24, 48. So it keeps doubling it. So you don't want to start with something. Oh, what happened? It died again. That's weird. What's it doing? Oh, I didn't make it. Oh, it was only supposed to, for this assignment. Oh, I thought I was going to create the 1 gigabyte file. No, I'm only creating one that's 50 megabytes right now. Okay. So right now it's only creating it. It only is making it up to 50 megabytes. I thought we were going up to 1 gigabyte. Yeah, because in the other folder we made it up to 1 gigabyte. Okay, so we're gonna stop with we got a 50 megabyte file now. Okay, all right. So we've got a 50 megabyte data file. Okay, okay. So it's now big.txt is 50 megabytes. Okay, actually, let me make it a little bit bigger. Let me make it a couple. Make it. Let me go ahead and make it a little bit bigger. 50 megabytes is a little bit too small. Computers keep getting faster. So 50. So this starts out 6, 12, 24. Let me make it a couple of steps bigger. Okay, so start with the 6 gigabyte, start with 6 megabytes again, and then okay, so what do we got? 200 megabytes. Okay, go over here and count that number of bytes. Notice how this program's taking quite a while to run. See, it took quite a while to run. Okay, time this. See how long it took to run. Time this. Okay, it took maybe around 10 seconds. That is, in fact, absurdly slow. That's insanely slow. That's not a very big file. It's a 100 megabyte file, and it took me 10 seconds to read it. Okay. Now let me go ahead and make it. Let me go all the way up to let me go up and get that file up to 1 gigabyte in size. So let me go here and go ahead and make it. There's the full 1.5 gigabyte size file. Okay. So I'm going to go ahead and I'm going to go all the way up to the full 1 gigabyte size. Now, if you read about computer hardware, you'll find that a computer these days can read a 1 gigabyte file in a fraction of a second. The amount of time it takes to read 1 gigabyte of data is a fraction of a second. I think I saw the other day that files are now reading on the order of like something like 20 gigabytes a second. I think that's the rough number, but it's many. The hard drive can read many gigabytes of data per second. Okay. Now I'm going to ask my program to read 1.5 gigabytes. Okay. And I'm going to see how long it takes. Yeah, but I got, let's see, almost up to 1 gigabyte. Remember, I just said that, yeah, Windows should create this file in a few seconds. Windows doesn't do very fast I/O. Windows is notoriously not very good at doing I/O in the desktop operating system. If you get Microsoft's database servers or web servers, they're very good at doing I/O. But the desktop operating system actually it's just kind of weirdly a joke. Yeah, it took it a long time to create that 1.5 gigabyte file. It should have actually, if the Windows operating system was using the same code that's used in the database servers, it would have taken probably 2 seconds to create that 1.5 gigabyte file, if that even. Okay, but it took almost half a minute to create it. Now I go over here and I want to read all the bytes in it. I want to count how many bytes are in that file. Okay, this program is going to run for a very, very long time. We're not going to sit here and wait for it. It'll take several minutes for it to read 1.5 gigabytes. Okay. Now, question is, can I make it faster? Okay. I'm going to just close that. I can now. Can I make it faster? And the answer is yes. Make this buffer size 1,000. Okay. Right now, and then here I'm going to read. But now remember, I'm reading this many things of that size from here. So now I'm going to read 1,000 bytes. See, this is one. So I'm reading 1,000 bytes into here. Now, when it comes back, it'll give me a number from, say, 0 to 1,000. But if it read 1,000 bytes, then this thing's going to be 1,000. I'll add it in. If it read like 472 bytes, because it got close to end of file, it'll tell me how many bytes it read, and then I'll add those up. And then the next time, if I get a short read, if I ask for 1,000 and it gives me back 400, I add my 400. That's a short read. But then I go back over here and I do it again. The second time I do it, the short read will be a 0. So if you do 2 short reads in a row, the first one will be a short read because it hit end of file. The second one will just give you back 0. So so in a sense, I'm going to do one more read than there is really. I'll hit end of file and get a short read, but then I'll go back and do another read after I actually have the short read, and then on the second time I'll find out, well, there's really no more data there. If I wrote this a tiny bit better, I really should have wrote this as if this was strictly less than n. That's when but then I wouldn't be counting it. See, then I would drop out of the loop and not count the n. So right now it's doing one more read. It's actually doing a read that detects end of file, and then doing one more read after that. Okay, so I'm going to read 1,000 bytes at a time. Okay, now got to recompile it. Okay, now it's a version that reads 1,000 bytes at a time. Still taking quite a while. I thought that would speed it up a lot more. Oh, stupid me. Did anybody see what I did wrong? This is the trouble with not using an IDE. Does anybody see what I did wrong? I forgot to save the file. I made the changes and I forgot to save it. So when I compiled it, I compiled what's on the hard drive. I compiled the file on the hard drive is the old version, okay? Because I haven't saved it yet. So I've got to save the file. Now I can go over here and recompile it. Okay, so that should have recompiled it. Now run it. Let's see, I find my. There. See, it took 4 seconds. It sped it up by a lot. Okay, took 4 seconds to read that. To read that one, I read that 1.5 gigabyte file in just 4 seconds there. Okay, what if I make my buffer 10,000 bytes? Okay, recompile it. Run it again. Okay, a little bit of improvement. Went from 4 to a little under 4. Okay, a little bit of improvement. I don't know, let's try one more. Let's make it, now we have a 100,000 byte buffer. You know, our buffer is 100,000 bytes, okay? So what we're telling the hard drive to do is now to read from that file that many bytes. That's a big chunk of data. That's 100,000 bytes at a time. So we're telling it to read big chunks of data. Let's see if that now compile it, run it again. Yeah, notice that was about a 25% improvement. It went from about 4 seconds to 3 seconds. Now, if I go back to 1 byte buffers, if I run it, it would take, I don't know, maybe half an hour for it to run. So why does this make a difference? What is the buffer size is turning out to have a huge impact on how fast this program runs. Okay, the buffer size is a huge impact on how fast the program runs. If I give it a big buffer, and now it's kind of quirky, at some point, like the best way to do this is to go up by twos. Do a 1 size buffer, then do a 2, a 4, an 8, a 16, a 32, a 64, 128, and find out what buffer size actually starts mattering. Yeah, at what buffer size do things start matter? Like next one's 256, then 512. I think when you hit 512, things are already at that point kind of fast. Okay, so let's try a 512 size buffer. Compile it. Okay, run it again. Yeah, see, I already got I'm about 4.5. Okay, I'm about 4.5. Actually, let's drop it down 1 size now. 256. Okay, compile it. Run it again. Okay, a little bit slower, but I'm still in the ballpark of 4 or 5 seconds. Go ahead and next smaller size, 128. Compile it. Run it. What did I do? Compile it. Run it. Okay. Still not much change. What we're going to talk about in a minute is what these buffer sizes are influencing. What is it that let's see, let me compile it again. Let's find there should be one buffer size that makes a pretty big difference. Okay, starting to get a little bit longer. 32. Okay, notice how it's creeping up. The amount of time it takes keeps creeping up. Okay, 16. Creeped up a little bit. Notice that it's creeping up a medium amount. Okay, try 8 byte. Okay, notice that it kind of jumped. It made a kind of a big jump at that point. It took 12 seconds there. Let's just do one more. Let's do 4 next. Almost at the, we're almost back down to a 1 byte buffer at this point. It went from 8 to 12. This time, see, now it's close to doubling each time. See, now it's 21 seconds. We could try it too. Yeah. If it doubles, it should take, this time it probably will double. So it would be around 30 or 40 seconds. And the question is, what is going on? What's changing in the operating system? What's causing these different amounts of time? We're doing the same amount of work. We're counting the number of bytes in a file. So we're not doing more or less work. We're doing the same amount of work. We're organizing the work in a different way. But the buffer size is, in a sense, organizing the work, not changing the amount of work. Okay. All right. So see, it doubled, okay, to 40 seconds. So if I went now to the 1 byte one, actually now I know probably how the 1 byte one was probably taking about a minute and a half. I thought it was actually longer than that. So probably if I go back down here to 1, it's going to probably double. You can just let it, run in the background, compile it. Okay, this one, we'll let it run in the background, but it's probably going to be about a minute and a half. Okay, now let's go look at the code. Now, to understand what's going on while that guy's running, we're going to draw a picture. Okay, the key idea is this jump between user space and kernel space. Okay, the key idea is how many times did the program jump from user space to kernel space? That's actually the key determinant of the runtime of that program. It wasn't really the buffer size that was important. It was the number of times you jump from user space to kernel space. The jump from user space to kernel space is incredibly slow. So if you do a lot of jumps between user space and kernel space, your program's incredibly slow. You need to minimize the number of transitions, the mode transitions from user space to kernel space. Okay, so here, let's draw another picture. Let me start paint up and I can draw another picture, kind of give you a sense of what. Now, here's the picture I want to draw. I've got a CPU over here. Okay. So here's a CPU, CPU. And the CPU has got a little mode bit in it. So the CPU can be in user mode, kernel mode. So that'll be the mode bit. It's either 0 or 1. Okay, so there's the mode bit inside the CPU. Okay, now I'm going to draw memory kind of abstractly. Okay, over here, I'm just going to say that memory is divided between 2 halves. There's the kernel space, and there's, on the other side, this boundary is going to be user space. So I'm thinking of memories being divided into, oops. Okay, so I'm going to abstractly think of memory as being in 2 parts, the kernel space and the user space. If the CPU is in mode 0, well, let's see, which way did we have it before? I had 0's kernel mode. So over here, we'll think of 0 as kernel mode. If you're in kernel mode, you're running, this half of memory, and 1 is user mode. Okay, and over here, this is I'm thinking of this as memory. Okay, so if I want, I can maybe just think of this as one big box. Oops. So memory is this big box, but it's divided into two pieces, the kernel space and the user space, okay? My code sits down here. So the fread function down here would be my code. So here's fread. Okay, there's my fread function call. Okay, in fact, make it readable. I'll just copy. So think of it this way. There's the fread function call. Okay, so that's down here. Okay. Now, what else is down here? What's important, what else is down here is this buffer. See, this buffer is sitting in memory. Now, remember, that code creates the buffer, but we really want to think of the buffer as a region of memory. So what I'm going to do is I'm going to think of it as down here, there's a region of memory that is the buffer. So that's the buffer memory. Okay, that's the buffer. Okay. So fread is going to put data in this buffer. So think of this abstractly. This is a cheap piece of code, and this piece of code creates this chunk of memory, but it's in user space. Okay. Then I have a hard drive over here, say with data. So there's the disk drive. There's the hard drive that holds the data. Okay. Now, up here is the system call. Okay. Now I'm actually running on the Windows operating system. So the system call that fread is a C function. Remember, I said scanf calls fread, but what fread calls on Windows is the nt read file system call. Okay. Actually, I won't show it. I'll just show it as like this. It's a system call. It's not really a function. It's kind of an abstract function. It's an operating system function. So fread calls nt read file. Oh, I didn't spell that right. Okay. fread calls the nt read file. nt read file. ... Okay, that's the sys call. Okay. Now, this guy actually asks for data from the hard drive. Okay. Where does he put the data? Well, it turns out he has his own buffer. So nt read file has his own buffer here, but it's in kernel space. Okay. And so this is another buffer. This would be a buffer, an array. Okay, buffer is a fancy word for an array. So there's a buffer in kernel space. And what nt read files tells the hard drive do is to take data off the hard drive from some file and put it in this buffer. Then when the hard drive has filled this buffer, then nt read file can transfer that data back to here for you. Okay, so there you call fread. fread calls nt read file. But when you do that, the transition from here to here is going from user space to kernel space. It involves this mode switch. nt read file creates a buffer, asks the hard drive to fill the buffer. While the hard drive is doing that work, it puts your program to sleep. When this buffer is full, the hard drive signals the CPU, and then the CPU knows that this buffer has been full, and it puts your program back, puts it in the ready mode. When your program gets back on the CPU, nt read file still got work to do. It needs to copy this buffer into here for you. Then when nt read file is copied here to here, then nt read file can return to fread. That would be the mode switch from kernel mode back to user mode. Okay. Now I said a lot of words there, and you should kind of review these steps in your head, because this is a real fundamental part of programming, is what's going on here. Remember, your function calls this guy and says, I want the data to put here. So you think the data goes from here to here, but it doesn't really. You know, but essentially, you're thinking that the hard drive data is going to be put there. But that thing calls that system call. But that means you transition from user mode to kernel mode. This guy creates his own buffer, tells the hard drive to put the data in that buffer. Then this program gets put to sleep. Essentially, your program gets paused. The hard drive is now working. It's copying data from a file into that buffer, and it can do that without the CPU's help. The hard drive can write data into memory without the CPU's help. That's an important feature of modern hardware. So the hard drive is putting data in here for you. Okay. Now, at some point, all the data has been, as much data as you asked for has been put here. Okay. When this thing is full, this guy is woken back up. NT-refile realizes that this thing is full, copies the data copies the data in kernel mode. It copies data from kernel space into user space. But this is being done by NT-refile while in kernel mode. When NT-refile has finished copying its buffer to your buffer, then it knows all the work is done, and NT-refile can return to fread, and then you finally go back from kernel mode to user mode, and your program has got its data in this buffer. Okay. Now, in our case, we're reading 1 byte at a time. So we're asking for 1 byte from here to here. Now, here's how NT-refile does this. Okay, so we're asking for 1 byte. Okay, here's what NT-refile does. This is a 1 byte buffer. NT-refile sees that you want 1 byte. NT-refile is not an idiot. NT-refile is not going to ask the hard drive for 1 byte. In fact, you can't ask the hard drive for 1 byte. It's the hard drive doesn't work in anything less than 4,000 bytes at a time. The actual minimal amount of data you can ask for the hard drive is 4,000 bytes. Okay, so that's called 1 sector. So NT-refile asks for at least a sector's worth of data from the hard drive. Okay, so it gets 4,000 bytes. Okay, then when the 4,000 bytes are here, NT-refile gives you 1 of them. Okay, right? Now you count that byte and you call fread again and ask for another byte. Now this is where things gets interesting. NT-refile says, well, I've got 4,000 bytes in the buffer. I gave you 1 of them. I still got 3,999 of them left. So it doesn't call the hard drive. It just says, here's 1 more byte and puts 1 byte in here. Then you count that byte and you ask for another byte. You go back here to NT-refile, and NT-refile says, well, I still got 3,998 bytes left. So it gives you 1 of them right away. Okay. So now 4,000 times you go back and forth here, copying 1 byte from here to here. But that's 4,000 transitions between user mode and kernel mode. That's what's taking a long time for the program to run. That's actually where all the lost time is in the program. 4,000 transitions between user mode and kernel mode. Okay. Now, when this buffer is finally empty, after you've done 4,000 calls here, this buffer is empty. So at that point, when you do 1 more call, NT-refile says, oh, my buffer is empty. I now go to the hard drive. Now, notice that means, this is real important. When you do a fread to NT-read file, you do a mode switch from user mode to kernel mode. You may or may not get blocked. If the data you want is in this buffer, NT-refile gives it to you right away. So the only price you pay is a user mode to kernel mode back to user mode transition. But the data was in the buffer. If you call fread and NT-refile doesn't have enough data in the buffer, it has to get it from the hard drive. That's slow. So that's when it puts you to sleep. So a call to fread always causes a call to NT-read file, the system call. The system call may or may not cause an IO operation. If the data is in this buffer, there's no need to do another IO operation. This call can be satisfied with just copying data from here to here. So then the only price you pay is the user mode to kernel mode back to user mode transition. But at some point, this buffer will be empty. And then when you make another fread, NT-read file will see, I have no more data in this buffer. Then it calls the hard drive, but that's slow. So then NT-read file has the operating system put you to sleep at that point. Okay. Now, when we made our, let's go back to that guy that was running. See, 14 seconds. Okay. Or no, 1 minute and 14 seconds. Okay. Notice that as I as I decreased the buffer size, remember what we were doing is we were decreasing the buffer size from 256 to 112, 64. We went all the way down to a 2-byte buffer. And well, actually, no, we went back to a 1-byte buffer. The program basically doubled in speed. The program kept taking twice as much time to do. Because from the point of view of analysis over here, what we're really doing is twice as many system calls. Okay. When we switched from 4 to 2 to 1, each time we did that, we doubled the number of system calls. When the buffer size was 8, we're asking 8 bytes at a time from here to here. Okay, well, 8 bytes is way smaller than this buffer size. So it just does 8 bytes here to here, then 8 bytes here to here. What we're counting, what took this program a long time, was those transitions. This took twice as many transitions because we were only asking for 4 bytes from here to here. Then this one took twice as many transitions again. The program's time doubled each time as we went down this way. The program size doubled because we're constantly increasing, we're doubling the number of system calls. Okay. Now up here we didn't see doubling because the size of the buffer is big enough now that you're approaching the limiting speed is not the transitions from here to here. The limiting speed is the transitions from here to here. See, once you get the size of this buffer being roughly the size of a sector, which is 4,000 bytes here, then you copy this buffer to here. Then the next call needs another buffer from over here. Then you copy that buffer. So if I go all the way up to say, if I go up to 4,000, 4,096, that's a sector size. So, you go 1024, 512 to 1024, 2048. Okay, this guy is the sector size. Okay, that is 1 unit of what the hard drive stores. Okay, so when your buffer size is this size, essentially what you're saying is, when you do the F read, you're saying get 4,000 bytes. Well, 4,000 bytes is exactly 1 sector from the hard drive. So the hard drive copies 1 sector to here, then that 1 sector is counted down to here. Then you want 4,000 bytes again, you have to go up to here and over to here. Now, suppose you double it again to 8,000. It will not speed up your program because now you're asking for 2 sectors at a time. 2 sectors up here means 1 call to the hard drive for 2 sectors. But at this point, what's slowing you down is the calls to the hard drive. And the fact that you make half as many calls to the hard drive when you do this versus this doesn't have much effect. The calling the hard drive is just so slow. It doesn't really matter if you call it 10,000 times or 20,000 times. It really doesn't have a big difference in time. It doesn't make that big a difference. The calls to the hard drive, once you're making the calls directly to the hard drive, it just takes a certain amount of time to read the data off the hard drive, and that's the limiting factor. The system calls no longer become a limiting factor. The hard drive becomes the limiting factor. So somewhere around here, the system calls stopped becoming a limiting factor, and the calls to the hard drive became a limiting factor. Down here, it was counting syscalls that's the limiting factor. Okay, we're actually counting how many system calls we're making, because we're actually saying, because now when the buffer size is 4, well, there's 1,000 of those in a sector. So the NT read file will get 1 sector from the hard drive. That's 4,000 bytes. That's 1,000 system calls of 4 bytes each. Those 1,000 system calls dominate everything. Okay. Now, what does that mean? From a programmer's point of view, you don't read files 1 byte at a time. And you'd be amazed how much professionally written program makes this mistake. It's well known that this is a common mistake among programmers who don't really understand how the I/O system works. They think I need to read a file and look for I want to look for a period. How many the first byte the first period at the end of a sentence. You know, you think you're going to read a file and look for something in the file. So you think, well, I'll read a byte and check what it is, and I'll read a byte and check what it is. And that turns out to be brutally slow because of these system calls. You're actually asking for 1 byte from here. So the IO system reads a sector from here to here, and then you do system calls to read 1 byte from here over to here. Or even if it's 10 bytes from here over to here. You know, remember we saw that we didn't see things start to really improve until we got to somewhere around here with the buffer size. A 1,000 byte buffer is a good buffer size. A 4,000 byte buffer is pretty good because that's the sector size. Okay, if I go back to my program here, let me put a 4,000 byte sector. Okay, 4,096. Okay, that my buffer is now the size of the sector on the hard drive. Okay, run the program. We'll compile it first. Run it. Okay, 4 seconds, right? Double the size of the buffer. Okay. Let's see. Actually, the easiest way to double it now is just 2 times. Okay, that's not the right number. What is 2 times 4,000? It's 9. Was it? Does anybody remember what? I forget what number that was. Okay, just double the size of the buffer. Okay. Compile it again. Run it with a twice as big a buffer. Not that much effect, you know, not that much effect. Certainly didn't have the time. Okay, go ahead and double it again. Yeah. Now what's really changing now is not so much the number of system calls, the number of times I have to read from the hard drive. You know, at this point, the NT read file, I'm asking for 4 buffers. I'm asking for 4 sectors at a time. So I'm asking for 4 sectors at a time. So NT read file will actually ask the hard drive. It won't ask the hard drive for 1 sector, then ask the hard drive for another sector, then ask the hard drive for another sector. NT read file will ask the hard drive for 4 sectors at a time. And it'll make this buffer big enough to hold all 4 sectors. And then it'll copy that over to here. Okay, so, but this isn't going to have a very huge effect on my program. The runtime. Compile it, run it. Okay, not much. Yeah, and if I start doubling my buffer size now, it's going to make my program a little bit faster. I mean, every time I make, because now I'm making fewer calls to the hard drive, but since calls to the hard drive are so slow, and since you get put in the blocked state and all this other stuff is going on, the fact that you make 100 calls to the hard drive versus 200 calls to the hard drive isn't a big difference. But making 200 system calls is twice as slow as making 100 system calls. The system call interface is really worth paying attention to. The number of times you go to the hard drive isn't such a big deal. So here at this point, it doesn't, I mean, once my buffer hits about this size, it's not going to make much difference if I increase my buffer size. It just, now I'm limited by just how fast my hard drive is. And some other issues. There are ways to make the program faster. Yeah, I can make this program faster, but not by increasing the buffer size. I have to do some other things to make this program get faster now. So naively, this is horrible. Buffer size is down like this. I'm killing my program with system calls. Okay. Now as a programmer, I may not realize that, but I'm killing my program with system calls. Okay. And then what I need to do is increase the buffer size. Okay. And then if I increase the buffer size, I can get dramatic increases in performance just by changing the buffer from, say, 1 up to, say, something medium size like that. I'll see a huge increase in performance if I go from a buffer size of 1 to a buffer size of 512. Or if I go from a buffer size of 4. Say, suppose I think I'm reading ints. So I read 1 int at a time. That's bad news. each int, well, it's 4 bytes, but that's still a lot of system calls compared to reading that many bytes, that many ints. Okay, that would be a lot of ints at a time. This would be 1 int at a time. You don't want to read from a hard drive one. If you have a file full of integers and there's millions of integers and you want to find the largest one, don't read the file 1 byte at 1 int at a time. If you read the file 1 int at a time, if you do this by reading 1 int at a time, you'll end up with a brutally slow program. You need to read, you know, a bunch of ints at a time and then process them. Okay, now that can be hard to do. If I read that many bytes, I have to break it up into ints myself because F reads real low level. It doesn't know anything about ints. It just put a bunch of data in my buffer. So then I'd have to know how to find the ints, which are 4 bytes each in my buffer. That's why I would want to use scanf. You know, scanf, I don't really want to use fread. I'd rather use scanf. Scanf will create its own buffer for you, and it'll make sure it's a good size buffer. One of the secrets is that if you write scanf and tell scanf to read a file 1 int at a time, scanf is clever enough to create its own buffer. Okay, actually, let me just put one last thing in this picture and we'll quit. The scanf function is actually here in user space. So if I were to call scanf, fscanf, that's really here in user space. So if my program calls fscanf, fscanf will create its own buffer in user space for me. It's kind of a hidden buffer, but it's there in user space. And then when it makes the system call, then fscanf will call fread using fscanf's private buffer, but it'll be smart enough to make that buffer big. Okay, fscanf will be smart enough that when it calls fread, it'll use a large enough buffer size that it's not going to do something dumb. So even if you told fscanf to read 1 int, fscanf will call fread saying read a couple hundred ints. Okay, so fscanf will, what we say, buffer things for you. It'll create its own buffer that it'll use in the call to fread, so that this buffer is not the minimal size buffer, it'll be a medium sized buffer. So fscanf will give you reasonable performance. Okay, so fscanf creates its own user space buffer. So it's a better function to call than fread. Fread, you have to create the user space buffer, and if you're not careful, you can goof it up. Okay, but notice that the key idea here is it's the number of system calls. But you have to draw this you have to really think hard about this picture to understand what's going on. That the size of the buffer, if it's too small, I have to make a system call to here to get, you know, if this is just a 2 byte buffer, system call 2 bytes, system call 2 bytes, system call 2 bytes. 2 bytes don't call to the hard drive. NT read file is never going to call the hard drive for 2 bytes. You know, it waits till its buffer is empty before it calls the hard drive. But so when you're getting 2 bytes at a time, the limiting factor is that you have to go user mode, kernel mode, copy 2 bytes, user mode, back to kernel mode. The transition from user mode to kernel mode is incredibly slow. Okay. All right. So we'll play a little more with this on next week, because there's actually, this was using the C library. And then I just wrote a couple other versions of the same thing. Like this uses Windows. Instead of calling a C library function call, I call Windows library function call. So I'm using read file, but it still does the same thing. It calls NT read file. So here I'm using this in user space, but it still ends up calling the same kernel file. But the code is written a little bit different. So, you know, compare C library function to a Windows library function. And then if you want, this one won't compile on Windows. That's a Linux function. This is actually meant to be a Linux program. This will compile on a Linux machine. This one won't compile on a Linux machine. The C library function will compile on both Linux and Windows. That's what it means to say it's a C library function, a library program. This compiles on both Windows and Linux. This compiles only on Windows. This compiles only on Linux. This one calls fread, which calls on Windows read file, which calls NT read file. This one, on a Linux machine, this one calls read, which calls the read system call on Linux. So on a Linux machine, this function is written in terms of this function. And on a Windows machine, this function is written in terms of that function. That's the C library function. And those are the lower level operating system functions. And each one of these makes the system call. This one makes the system call to NT read file. This one makes the system call to the equivalent of NT read file in Linux. Okay, so we'll play around a little bit more with this on next week and just do a little bit more comparison, because this is a real important idea. This is why we want to understand system calls. Yeah, so that when you write programs, whether it's in Java or any language, you don't do dumb things. Like, you have to understand how this operating system is really doing things so that you don't make lots of little system calls. It's a fairly common mistake. It's surprisingly common to find out that a company's written their code doing something like this, and they don't understand why their software is so slow. Okay. They don't realize that they got wrong size buffers and they're making too many system calls. Okay, so we'll quit there. Anybody have any question? Okay. Play with these, run these experiments on your computer. Play with these buffer sizes. See how they affect your computer. You'll get slightly different numbers than I got, because we all have different hardware. So you should get ballpark numbers similar to mine, but you may have a faster laptop. Your I/O system might be faster than this one. You may have a CPU that even does system calls slower than mine does. Some CPUs are slower at doing the user mode, kernel mode transition than others. Okay, so we'll quit there, and we'll do a little bit more with this on Monday, and then we'll start talking about Windows scheduling. We'll start talking about the operating system scheduling theory. Okay, so if you have questions about there'll be a homework assignment up there pretty soon using this kind of stuff. Okay, so you have a good weekend. Bye.